So this second talk will be presented by Miguel Ángel Rodríguez. He comes from the University of Valladolid, and his talk is entitled "From the Microscale to the Nanoscale in Cellular Materials."
Okay. Well, good morning, everyone. First of all, thank you for the introduction. And I would like to thank you, the organizers, Eugenio and Mariluz, for inviting us to be here today. Well, my topic is about cellular polymers and how these materials, how the properties of these materials are modified when we move from the what we call microscale to the nanoscale for this type of materials. Well, as probably you are not very familiar with cellular polymers because it's a very specific topic, I will explain a little bit about I don't know if this has, yeah, about these materials at the beginning. Then I will go into the properties and how these properties are modified when we move to the nanoscale. And then if I have time, I will discuss a little bit about how to produce these materials, which is also something interesting from the point of view of nanotechnology. And finally, I will summarize the key findings. Well, cellular polymers are a specific type of materials in which we have a combination of a solid material, and in this case will be a polymer, and at a gas phase, we will have a gas phase. So we are dealing with two phases materials in which we have introduced by purpose in a controlled way a gas phase into the solid polymer. Well, these are well-known materials. They have been developed for many, many years. And in fact, these type of materials are all around us. They have interesting properties such as very low density, good thermal insulation, high mechanical properties in comparison with the density, etc. So they are around us in many, many different applications. They are also known as polymer foams. So I'm sure you are using these materials every day in your daily life. In fact, 10% by weight of the plastic consumption in the world is used to produce this kind of material. So they have been very successful materials in current history of technology. These are the general applications. They are also used in very niche applications with very technical requirements, such as, for instance, gas separation or oil spill remediation, electromagnetic shielding. So they are around us in many different areas. So as they are two-phases materials, and they have a complicated structure that can be studied at different levels, in fact. So this will be an SEM picture of a typical low-density cellular polymer in which we have the cells, so the gas phase inside the very thin membranes of the solid polymer. So one of the levels of the structure is how these the cells are, let's say the cell size distribution, the anisotropy of the cell. So that we will describe in this initial level the gas phase, how the gas phase is distributed in our material. But on the other hand, we have the solid phase. The solid phase in low density materials are located in the cell walls and edges of polyhedra. So how this material is distributed between walls, edges, struts, etc., and the thickness of this solid phase is also important. Finally, we have a polymer. And the polymer itself has its morphology. How the morphology of the polymer will influence the properties. If we have crystallinity, what is the degree of crystallinity, the size of the crystals, etc. How finally the polymer is organized at the nanoscale will have an influence. So as you see, well, as many other materials, this is quite complicated. And there are many parameters that we can look at to analyze the structure. And all these parameters will have an influence on the final properties. In some or other way, they will play a role. Well, basically, my talk today will deal with cell size, the size of the cells, and the cell density, which is related. I mean, the amount of cells we have in a cubic centimeter that will be related with the size of that cells and the relative density of the material. Basically, current technologies, introduction of the production of these materials that are produced at industrial scale, of course, have typically the cell sizes produced at industrial scales are very large. Let's say higher than 100 microns. As a minimum, you can find phones with or cellular polymers with cell sizes by 100 microns, 1 millimeter. So they are quite large. So this has been, of course, one of the topics of research in the last few years: how to control this cell size and what happens if we go to smaller cells. Okay, that's basically what I will discuss now. So let's move from the micro scale means 100 microns, 200 microns, 10 microns, etc., to the nanoscale. This is basically a very short summary of the history around these materials. Current technologies, industrial technologies, sizes, cell size is very large, as I said before. Then in the 80s, 90s, some technologies were developed to reduce the cell size, keeping the density, keeping the amount of gas. I mean, we want to have a lot of gas in the material for many applications. So keeping the density of the material, reducing the cells to 10 microns, for instance. This is what it is called microcellular foams or microcellular polymers. These are already available at industrial scale. Several companies have upscaled these technologies, developed in the 80s, 90s. Then, well, around 2000 to 2010, some papers appear in the field of what is called nowadays submicrocellular polymers, cell sizes in the range of 1 micron, around that. And in the last 10 years, our group and other groups around the world have been working on reducing the cells even lower to values, well, it's difficult to say the number, but as small as possible. And the change in properties, and some of the properties appear when the cells are around 300 nanometers. For that reason, I write here 300 nanometers. This means cell densities around 10 to the 13 cells per cubic centimeter. You mean that here we start from 10 to the 9, and in current technology, we have 10 to the 6. So we have to increase a lot the number of cells in the material. Okay, so well, basically this is the trend we have followed in the last years. So we can say maybe we are improving the cellular structure, at least from the point of view of reducing the cell size, and we expect some improvements. Is what we expect. Maybe we will find something interesting here. Some non-expected properties are expected also, theoretically, if we reduce the cell size. Okay, this concept was proposed 10 years ago, more or less, but it was not possible to check that concept because it was very difficult to produce materials with low densities, very high cell densities, and low cell sizes. So, so that's a nice idea, but no proofs of that until the last 10 years. So one of our topics in CellMat in our group has been producing these materials, finding ways to produce large samples of nanocellular polymers, and testing the properties, and trying to investigate if the properties are better or not. So let's say from the microstructure point of view, a cellular polymer with nanocells or with cells in the nanoscale have two interesting, at least theoretically, we can say that there are two interesting expected behaviors. But because on the one hand, the gas phase, so the gas is inside the cells could be closed, for instance, and then the gas is inside the cells. So the cell size could be, for instance, between 50 and 300, although later I will have some materials with lower cell sizes than this. And these values are around the mean free path of air at atmospheric pressure and room temperature. So we are in similar values. And it's very well known from thermodynamics that this changes the way the molecules interact each other because they are kind of confined in a small space. This is known as Nanoscale effect. And basically, the interaction between the molecules inside these very tiny cells is much smaller than when the cells are larger. So, for instance, there will be a very low transmission of heat when the molecules are in vibration. So this is one expectation. We will have Nanoscale effect, and this will translate in a modification of, for instance, the thermal conductivity of the material. This is one of the things that we will now check with experiments. And the other thing we could expect is that a cellular polymer is, of course, a material with cells, or a nanocellular polymers with cells in the nanoscale. But at the same time, to have cells in the nanoscale, we need cell walls also in the nanoscale, really tiny cell walls, at least for this topic. Something like maybe between 10 to 50 nanometers, something that is real. When we produce these materials, we find this kind of very thin cell walls. You have to consider that the material is a polymer. So it's a material with a very high molecular weight. And due to this, the molecules are very long, even longer than the cell wall thickness. But it means that we have created a kind of material consisting of very thin films that are in some way confined because the polymer molecules are larger than the thickness of these films. So we will have kind of, we call this confinement of the solid phase because the molecular organization will be different in this kind of material than in a solid polymer with a higher thickness. Well, saying that, I will show you some examples of physical properties that are modified when we go from micro to nanoscale. So basically in our lab, we can produce the same material, same relative density, same amount of gas with cells in the microscale, maybe 10 microns, 20 microns, 100 microns, and cells in the nanoscale. That is something we can do. I will show you later how we produce these materials. So then we can compare. I mean, it's very easy. We produce the materials, and then we compare the physical properties. And then we try to understand what happens. Regarding thermal conductivity, that is a very important property because we need thermal insulators for everything, especially today that we want to have low energy consumption in the buildings. So we need to isolate properly the buildings. So thermal conductivity is a very important property for us. And here we are comparing well, for instance, you have here some nanocellular polymers produced in our lab. This is a polymer with an average cell size of around 200 nanometers. And this is a polymer with an average cell size of 24 nanometers. And this is a microcellular. All of them produced with the same material, PMMA, polymethyl methacrylate, similar relative density. And as you see, thermal conductivity versus relative density, we have a decrease as expected, because when we decrease the density, we reduce the amount of polymer, and the gas has a lower thermal conductivity. And as you see, there is a reduction. This is the microcellular polymer, nanocellular with this cell size, and nanocellular with another cell size, smaller. So we are reducing the thermal conductivity. In particular, we can estimate the thermal conductivity by modeling, well, very simple analytical models to estimate the values as a function of the cell size for a given relative density. So this is what happens. And we have experimental evidences of this. So this would be the values for 10 microns, microcellular material. And when we go to nanocellular material, due to the Nanoscale effect, basically the conduction of the conduction through the gas phase is reduced, and then the thermal conductivity of the material is reduced. So by producing these nanocellular polymers, we have a strong change, and we move from typical values of thermal conductivity around 30, 35 milliwatts per meter per Kelvin that are the thermal conductivity is a typical value for current materials in the market. We can reduce the conductivity clearly below 25, which is the conductivity of air, which is a new class of materials named as superinsulating polymers. So, well, this is very interesting. It's one of the key topics in nanocellular polymers is the driving for this topic. People is looking for developing super insulators using a simple technology that could be a scale up. So that is one very interesting option. Then transparent cellular materials. Well, basically all cellular polymers are opaque. Basically, because even if the polymer is transparent, you have PMMA, which is transparent, or polyester, they are transparent. You make a cellular polymer and the material is opaque. Basically because when light tries to pass through the material, there is scattering. There is a strong scattering in the microcellular cells. So at the end of the day, you have all forms, all the cellular polymers are opaque. This is our general rule. Instead, if the cell size is much smaller than the wavelength of light, that's the key concept here. So basically, when the scattering center for the light is 1/10 in size, the wavelength of light, then we move from scattering, the normal one, to Rayleigh scattering. And Rayleigh scattering is much smaller, is a scattering that is less intense. So we can create, if we reduce the cell size to a value of around 50 nanometers, because wavelength of light in average will be 500 nanometers, so 1/10 is 50, we can make nanocellular polymers that are transparent. Here you have some examples produced in our lab. So, sorry. Here we have 3 materials with the same relative density, so same amount of gas, more or less. Let's say this is 60% gas. This is relative density, so this is the solid fraction. Gas fraction would be 1 minus this. So we have more or less the same gas fraction. Different cell sizes, the same thickness. Thickness of these materials is very small, around 0.5 millimeters. You see, when the cell size is not too small, it's 220 nanometers, is very small in comparison with commercial materials. We have opaque material, even for this very small thickness, due to scattering. We have scattering in this material, no translucent at all. But when we move to very smaller cells, you see we have some transparency in the material. So we have created, in this slide, transparent materials that at the same time are very good at thermal insulation, and they have very good mechanical properties. So this is a kind of combination of properties that is not easy to reach, because we have transparent materials, silica, PMMA, but they are not thermal insulators, okay? Or we have silica aerogel. This is transparent, but the mechanical properties are very poor. So here we have a different material to others in the current literature, let's say, scientific literature. So this is really interesting, and one of the most interesting properties of nanocellular polymers. Then we have one question is, if we have a microcellular polymer with a given relative density and we produce the nanocellular, what happens with the mechanical performance? So we have tested this extensively, I would say. We have seen, I will focus on this because these are other from the literature, other research from some colleagues in different countries. But here you see, this is the toughness. So the energy you need to break a sample, basically. The energy needed to break the sample. These are the microcellular materials. Cell size is 50 microns to 1 millimeter as a function of relative density. These are microcellular. Cell size is below 10 microns to 500 nanometers. And then you have materials with less than 100 nanometers. You have a clear improvement of the mechanical performance. Okay. Well, understanding this is not so simple because you need to go into the deformation mechanisms, the molecular structure of your polymer, blah, blah. It's not so easy, but we are working on that. But basically our hypothesis to explain this is what we call confinement. When we have the microcellular material, we have a different organization of the molecules at the nanoscale than when we have the nanocellular material. In fact, and related to the previous one, we have seen that the glass transition temperature of the polymer, in this case PMMA, increases significantly when we make nanocellular polymers. So we have the polymer, It has a glass transition temperature characteristic of that polymer. If we make a nanocellular polymer with this polymer, the glass transition temperature is much higher. So energy needed to activate molecular movements has increased by 10 degrees C, which is very high, in fact. So we have a different organization, and this is probably the reason for this much higher mechanical performance. And well, other potential applications for these materials are due to the very high specific surface. Of course, if we have cells in nanoscale, and in this case, it's another type of material produced in our lab with a completely open cell structure. This kind of structures could be very useful for catalysis, for sensors, membranes, etc. This is something is still not analyzed in detail. Okay. So, well, the answer to the previous question I mentioned before is, okay, we can produce these materials, but are they interesting in terms of physical properties? And well, the answer is yes. I mean, we have materials that can combine some very interesting properties such as low density, super insulation. They can be translucent, excellent mechanical properties, high surface area. So it's an interesting topic, okay, to focus on that. Well, I'll speak about a little bit about the properties, okay, just to motivate you to discuss a little bit about how to produce these materials, which is not so easy. So I will speak briefly about how to produce nanocellular materials. Well, nanocellular polymers are known and has been produced by different methods: phase separation, imprinting, templating approaches. That is nice, and this has been done before. The main issue of these methods is that typically the thickness of the sample you produce is very small, and typically you use solvents, chemical solvents. As we want to produce, for instance, a thermal insulator to substitute a window, so remove this silica of the window and put our nanocellular PMMA, we need some thickness. We need maybe 4 millimeters, 10 millimeters, 2 millimeters, so that approaches are not what we want. So for that reason, we have focused our efforts on foaming, which is, of course, our main topic in CellMat. So this also have an influence on the decision. And this foaming allow us to produce thick samples, maybe 10 millimeters. In principle, the process I will show you, thank you, is environmentally friendly. So we will not use chemical solvents, we will use CO2, and in principle is scalable. Well, a foaming process, what is a foaming process? Very briefly, this is a video. We took this video with this equipment. We have an X-ray source, a detector, and we foam the sample in the middle of this system. So we can see with the X-rays, we see inside the material. So I will start the video. And during foaming, there are many things that occurs. First, we have nucleation of the cells. The cells are created. Then growing of the cells. And during growing, the expansion ratio increases, so the material expands. And then we have the generation. You see now the cells are disappearing. So we have coalescence, coarsening, drainage. Finally, we need to stabilize the material. So foaming is something tricky. There are many physical-chemical phenomena that take place during this kind of process. So these are the different aspects. And well, in the current technologies, cell densities are 10 to the 6 to 10 to the 9. That is the current state of the art in the industry, let's say. We need 10 to the 13. So we have to multiply we have to increase by 4 orders of magnitude the number of cells in the material. And if we go, that is about nucleation. If we go to the degeneration in current technologies, the generation ratio are between 10 and 1,000. So this means 1,000 means that you create 1,000 cells at the beginning of the process, you finally have one. Okay, so 1,000 cells disappear and just you reach one. Of course, if you create a lot of cells, but they disappear in the process, at the end of the day, you don't have the nanocells. So we have to be careful because we need to increase the number of cells as much as possible during nucleation, but we have to follow the criteria of keeping the cells. So one nuclei is just one cell. No, we need 10 nuclei to have one cell. Okay, so that is the strategy. And in order to do this, we have used gas dissolution foaming. I will explain very briefly. In gas dissolution foaming, we have a polymer. In this polymer, we introduce CO2 by just increasing pressure. So we put the polymer into a pressure vessel. We introduce CO2. The CO2 is dissolved into the polymer. Then we release the pressure, and then we have the CO2 inside the material. But as we have lower pressure now, the CO2 is oversaturated. So just by heating, we create the cellular structure. So the cells are nuclei, the cells grow, and if we are careful, we control carefully the process, the cells stabilize. There are two ways to create nanocells. One is by homogeneous nucleation, in which we use a pure polymer and we play with the saturation conditions, pressure, temperature, pressure drop rate. So very let's say, approach based on physical parameters. And the second way is introducing nucleating agents into the material. So design a formulation that chemically will make, will create a very high number of cells very quickly. So this is homogeneous nucleation. In homogeneous nucleation, we can move from microcellular structures to nanocellular structures just by increasing saturation pressure using PMMA and CO2. Very simple. The only problem is that you need a very nice pressure vessel with supporting very high pressures. But you can do this. If you have that pressure vessel, this is very easy. So you move from 10 MPa microcells, 30 MPa nanocells. Very simple. Other option, reducing temperature. By reducing temperature, we increase solubility. So here you have 30 MPa, 25 degrees C, 500 nanometers. 6 MPa, minus 32 degrees C, you have 10 nanometers. So by reducing temperature, you increase solubility, and then you have nanocells again. So also very simple approach, but you dissolve the gas at minus 30 degrees C. The diffusivity is so small that you need many hours. So the process is, let's say, not viable from a production perspective. Okay, so this is one examples of what we can produce. Also, we can play with the polymer. Different polymers with different molecular weights give you different nanocellular polymers. And second, I will show you the heterogeneous, just two examples. In the heterogeneous nucleation, we introduce into the polymer nucleating agents. Nucleating agents could be particles, for instance, sepiolides, nanometric sepiolides. Could be the mixing of two immiscible polymers, PMMA plus TPU, polymethyl methacrylate, MAT, thermoplastic polyurethane, or could be the combination of polymers that are miscible. I will show you just one example, which is very spectacular. Here you see, this is PMMA, microcellular, produced with 10 MPa and forming 100 degrees C 1 MPa. Well, 10 MPa is a high pressure, but not as high as before. In the homogeneous nucleation, I need 30 MPa. This is a micro. And these materials are produced with the same conditions, but I have introduced 1% TPU here and 2% TPU here. You see, density is the same, relative density is the same, but the cell size is much smaller. So here, by properly controlling the formulation, we can go from the microscale to the nanoscale using processing conditions that are easy to reach. Okay, so I will move to the final one because not I will not finish. So here is other examples controlling the nucleation by introducing micelles into the polymer. These micelles, every micelle is later one cell in this kind of process. So you see here the number of micelles in the polymer is the same as the number of cells. And well, here you see different materials we have produced in the lab, cell size, relative density with different combinations, different, let's say, heterogeneous systems. So we can control relative density, cell size. There are some regions that are difficult to reach, as the region here, but we can in some way to control everything. Well, just to finish, basically, I've been speaking about cellular polymers with a nanocellular structure, and the interesting structure of these materials and how they have different properties. As I said, they have an interesting combination of properties, difficult to reach with other materials. And we can produce these materials using both homogeneous and heterogeneous nucleation, using something that is can be upscale. We have developed all these production technologies. In fact, we are now working on the possibility of scaling up some of these materials to produce them in a larger scale than only in the lab. Well, just to finish. Well, thank you very much for your attention. Well, if you have any question, please go ahead.
So, are there any questions? Yes.
Thanks. Can you do this technique for every polymer, or which are the requirements? Like it has to be thermoplastic, or?
Yeah, thank you. It's a very good question. With the technology we are using, that is basically a combination of the polymer and the gas, it's really important to have a very high solubility. That is key parameter. So if you try to use polyethylene, for instance, you will need a gas with a high solubility in polyethylene. So you need to find the right combination. PMMA plus CO2 is very nice because solubility is very high. And then you can reach this kind of structure. If the solubility is not high enough, then it's very difficult to reach this kind of very small cells in the material. So it's kind of trying to find the right combination for every system.
There is another question here.
Hi, nice talk. I have the question in the cell synthesis that you use the carbon dioxide and you modify the pressure that you control the size of the cell. Have you tried where supercritic carbon dioxide?
Well, basically, depending on we are always over the critical pressure, okay. Always, because we are using 10 MPa, 20 MPa, 30 MPa. Even in the lab, we have 200 MPa now, 2000 bars. Sometimes the temperature is not over the critical. Sometimes we use very low temperatures, 20 degrees, minus 20. So we are not in supercritical conditions in many of the experiments. Because sometimes we don't want the material expands in the pressure vessel. So we want to keep the expansion for the second step. And for that reason, sometimes we use lower temperatures. But of course, if you use CO2 in supercritical conditions, basically what you have is a reduction in the saturation time. You reduce the cycle time by increasing the diffusivity.
Okay, thanks.
Yeah, you're welcome.
I think there was a last question here.
Then, well, nice results and
thank you.
Interesting, well, for applications also. Then, from the chemical point of view, you are using polymers that are already known.
Yes.
And then you try only to use one polymer, or you can also mix two polymers for having also different.
Yeah, in fact, for instance, in this example, we are mixing polymers. This is a blending of polymers. So. For instance, here we have a polymer, PMMA. PMMA is our, let's say, model system because it has high solubility, very low gas transition temperature. So it's very nice to work with this. And in this case, we are combining this polymethyl methacrylate with copolymers in which we have 3 blocks, methyl methacrylate, butyl acrylate, and methyl methacrylate. So when you do this, basically what you have is that the solid material, the PDA phase organizes in nanometric micelles. Mm-hmm. And as the solubility of CO2 in PVA is even larger than in PMMA, most of the gas is dissolved into this area and the cells are created in this area.
No, because playing with that, you can also reach hierarchical structures and these kind of things. The question was this one, because I don't know how much you control the possibility to have two kind of pores in the same material always.
That's something interesting, of course. Huh?
And then the other question is, well, you are not with the polymers, you are not introducing a lot of functionality in the polymer. I mean, the polymer is a structure.
Yeah, it's a structural material.
Creating the cell, but it's not. But how about trying with polymers that are more functional in themselves?
We have been trying, for instance, with conductive polymers, collaboration with Mariluz, and sometimes the difficulty is how to finding the right way to form that material. So this is very easy. When we move to other polymers, sometimes it's much more difficult. But it's something really interesting. So for instance, for sensors, this is quite interesting. You are able to, you have very high surface area. You are able to locate in the surface of the cell walls your sensor, let's say, your material with sensor properties. You can have very nice selectivity, etc. It's something that we would like to do that, but it's still not. It's still all in our minds.
Okay, thank you.
You're welcome.
So let's thank the speaker again.
Yeah, thank you.